Whether it's a paper plane you fold yourself or a fighter jet breaking the sound barrier, the thing that keeps them in the air is exactly the same: aerodynamic lift. It sounds simple, right? But the way most of us learn about it, well, it isn't quite the whole story. So let's get into the real science of how things fly. I bet you were taught that the magic is all in the curved top of a wing. The idea is that air has to travel faster over that curve, which creates lower pressure, and poof, you get lift. It's a really neat idea, but it's also kind of wrong. Or at least, it's a very incomplete picture. So let's start by totally busting this common myth. You'll find it in a ton of textbooks and science shows, but there's a huge fundamental flaw in the logic. One that a single, simple question can blow wide open. Yeah, this whole idea is called the equal transit time theory. It says that little particles of air that split at the front of the wing have to meet up perfectly at the back, and since the top path is longer, the air on top has to hustle to get there on time. It sounds perfectly reasonable, but here's the thing. There's absolutely no rule in physics that says those air particles have to have a happy reunion at the end. In fact, wind tunnel tests show the air on top moves way faster than this theory could ever account for. And that brings us to the real killer question for this theory. If lift only happens because of a specially curved top and a flat bottom, how in the world can a stunt plane fly upside down? When it's inverted, the curved part is on the bottom. At that point, the whole theory just completely falls apart. So yeah, let's dig into this upside-down test, because once you ask that question, it forces you to stop looking at the wing's shape and start looking at what the wing is actually doing to the air around it. And here it is, the real secret. Lift is all about deflecting a huge amount of air downwards. The curved shape of the wing definitely helps make that more efficient, but it is not the main reason a plane flies. The real star of the show is something called the angle of attack. So what is the angle of attack? It's just the tilt of the wing compared to the air it's flying through. You can feel this yourself. Stick your hand out of a moving car window. If you hold it perfectly flat, the air just flows around it. But tilt your hand up just a little bit and you feel it get pushed up, right? That's it. You just created a positive angle of attack and generated lift with your own hand. And this is exactly how we solve that upside-down paradox. When a plane is flying normally, its wings are tilted to push air down. But when it's flying upside down, the pilot just pulls the nose of the plane up a little more. Now, even though the plane is inverted, the wings still have that positive angle to the airflow. They're still pushing air down, which means they are still generating upward lift. It's that simple. Okay, so this brings us to the real physics behind all of this. And honestly, it has a lot less to do with the famous scientist Daniel Bernoulli and a whole lot more to do with Sir Isaac Newton. And you know what? It's actually beautifully simple. A wing is basically a giant fin that, when tilted, forces air down. That push is the action. And as Newton's third law famously tells us, for every action, there is an equal and opposite reaction. Well, that reaction is the air pushing the wing up. And that upward push, that's lift. So you might be thinking, okay, wait a minute. What about all that pressure difference stuff I learned in school? Was Bernoulli's principle just a total lie? Well, no, not exactly. The truth is, these two ideas are actually perfectly connected. As NASA themselves put it, both Newton and Bernoulli are correct. They are two different ways to create lift. They're just two ways of describing the exact same event. Think of it like this. Newton's explanation, deflecting the air down, is the cause, and Bernoulli's pressure difference is the effect. Because the wing pushes the air down, that air has to speed up as it goes over the top, and that is what creates the lower pressure. One causes the other. Okay, but there is one last piece to this puzzle. When a wing is tilted, why does the air flowing over the top even bother to follow the wing's curve downward? Why doesn't it just fly off in a straight line? The reason is a funky little phenomenon called the Coanda effect. It's just the natural tendency of a fluid, and we have to remember, air acts like a fluid, to want to stick to a curved surface it's flowing over. This effect is what makes the air hug the top surface of the wing, which allows the wing to grab it and direct it downwards. And that's what's so essential for creating lift. All right, so now that we have the real physics down, angle of attack, Newton's third law, and the Coanda effect, we can start to make sense of even more complex flying machines like helicopters and supersonic jets. An airplane and a helicopter are trying to solve the exact same problem, just in completely opposite ways. You need air moving over a wing to create lift. So an airplane moves its whole body forward through the air to get that flow. A A helicopter says, nah, I'll just keep my body still and spin my wings through the air instead.
It's really cool how they're controlled. A helicopter pilot uses the collective to change the angle of attack on all the blades at the same time to go up or down. They use the cyclic to tilt the entire spinning rotor to move forwards or sideways. And that little rotor on the tail, that's Newton's third law again. The engine spins the main blades one way, so the body of the helicopter wants to spin the other way. The tail rotor just pushes back to keep it straight.
Okay, let's switch gears to a totally different challenge, flying faster than the speed of sound. This isn't just about having bigger, more powerful engines. It's about overcoming this enormous aerodynamic problem called wave drag.
See, as a plane gets close to the speed of sound, that's Mach 1, the air in front of it can't get out of the way fast enough. The pressure waves start to pile up on each other, forming these massive shock waves. And the result is this insane spike in drag, like hitting a virtual wall in the air. It takes a ridiculous amount of power to punch through it.
To get past that wall, engineers came up with some really clever tricks. They used sharply swept back wings, which kind of fool the air into thinking it's moving slower than it is. They also use incredibly thin wings and even shaped the whole body of the plane like a Coke bottle to smooth out those shock waves and reduce that wave drag. And all of this leads us to what might be the most important concept in all of aviation. Building an airplane isn't about making one part perfect. It's about making everything work together in a constant balancing act. The team at Boom Supersonic calls it the grand compromise, and that's the perfect way to put it. Every single choice an engineer makes, from the shape of the nose to the placement of the engines, comes with pros and cons that ripple through the entire design. Just look at how thick to make the wing. The aerodynamics expert wants the thinnest wing possible because that's great for reducing supersonic drag, but the structural engineer will tell you that a super thin wing has to be made much heavier to be strong enough. And the fuel systems engineer will complain there's no room to put fuel in it. A thicker wing is lighter and can hold more fuel, but it creates way more drag. The final design is always a trade-off. So, you see, from that little paper glider all the way up to the most advanced jets, flight isn't just one simple idea. It's this beautiful, intricate dance of forces, a constant compromise. And it really makes you wonder, what other incredible marvels of engineering are hiding all around us, just waiting for us to look a little closer?